This scenario in which the manager is trying to forecast the sale of project management software is a good example of a kind of problem that looks like it should be pretty simple, but it's a surprising amount of work, particularly the second half. Let's take a look. A manager's been using a certain technique to forecast demand for project management software. Actual demand is listed below and her corresponding forecasts. Okay, so what we're looking at here is 5 months worth of data. Now, the first part of this question, if the manager uses a 3-month moving average instead of her technique, what would her forecast have been for June? Okay, now 3-month moving average, that's simple. You just average the past 3 months. This half of this part of the problem, the key though is be very careful. What is it that you're trying to forecast? You're trying to forecast June. All right, now what is it that you need to be careful about? First off, you average actual. Don't accidentally grab the forecasts in the other column. And make sure that that actual is 45 for March, 42 for April, and 34 for May. Those are the 3 numbers that we are averaging together. I get 40.3. There's the forecast for June. Now that is pretty straightforward. Why am I stressing that? Because a very common error is people will accidentally grab the 48 for June and then back up. No, you can't average in the actual for something that you're trying to forecast and it hasn't happened yet. Anyway, so it's just May, April, March. Now that was only half of that part because then it asks what would have been her percent error. And we remember that percent error is the error, which is actual minus forecast, divided by the actual. Okay, so the actual in June was 48. See, now we need the 48. We go, all right, 48 minus the forecast we've just found, 40.3. Now be careful, divided by the actual again, or that 48. That's basically about 16%. If you're looking in the first edition of Simpson and Hancock, I believe it says negative 16%, and that's naughty. It's actual minus forecast. It is a positive 16%, 48 minus 40.3 in the numerator. Okay, now that actually was all pretty straightforward computations. The second part of this problem looks like we ought to be able to work at that quick, but take a closer look at it. If the manager used simple exponential smoothing with an alpha of 0.2 instead of her technique, what would the forecast for August be? All right, now I'm just making a note to myself again. What are we trying to forecast? Now we're trying to forecast a new month. All right, fine. Assuming that simple exponential smoothing did produce a perfectly accurate forecast in March. Okay. Now wait. Simple exponential smoothing is simple. It's a formula. Your forecast for a certain period, like a month in this case, equals your forecast for the period before plus some portion of the actual from that period minus the forecast for that period. This is just the formula. Oh, right. And it has told us or instructed us that in this case, that value right there is to be 0.2. Now, what it wants is the forecast for, I'm just going to abbreviate August. Okay, now that means that in order to calculate that, you need the forecast for July plus 0.2. That's the number we're supposed to use. Times, now the actual from July we have, right? That's what, 38? Minus the forecast for July. Oh, all right. So forecast for, I wrote T minus 1, but I mean July. Same thing here. Oh, all right. So we should be able to complete this pretty quickly. All we need is, now wait a minute, all we need is the forecast for July using simple exponential smoothing. The distractor here is the manager's forecast, right? We don't know what technique she was using. We're exploring a different one. And we don't have her forecast for July. We have her forecast for March. That's what it meant, and that's the key to unlocking this. Her forecast for March was perfectly accurate. You know, so best way to do this, so let's go back up here. These were distractors. Turns out, for these two problems anyway, we don't need them, because we're going to forecast over again simple exponential smoothing with an alpha of 0.2. Well, we're going to simulate it having been done. We don't have to worry about March because we're ever so helpfully told that in March it was perfectly accurate, which means it must have been 45. And that's when it's going to get us started. Because while we don't have right now at this moment everything that we need to forecast August, we now have everything, do you notice this, that we need to forecast April using simple exponential smoothing with an alpha of 0.2. Because the forecast for April would be, see if I can squeeze it all in there. Let's see, the forecast for April would be the forecast for March, which was 45, plus 0.2 times what actually happened in March, well that's 45, minus the forecast for March, okay, that's 45, meaning that this is 45 plus 0, 45. Ah, yes, the simple exponential smoothing forecast for April would have been 45 also. And actually the reason is because it was perfectly accurate in March, and that's what simple exponential smoothing does. If a forecast turns out to be perfectly accurate, it keeps it for next time. Anyway, you're saying I don't need the forecast for April, I need the forecast for August. Yes, but now that we have the forecast for April, we can calculate the forecast for May, and we have to, sorry. The forecast for May is 45 plus 0.2 times what actually happened in April. This is the forecast for May, so you go up to the row before. Well, it was actually 42, okay, minus 45. I get on my calculator that the forecast then for May using this technique would be 44.4. Okay. You say, well, I still don't need May, I need August. Yes, but now we have the means of forecasting June, and unfortunately we have to. Because we say, well, that was the forecast for the month before, which is May, which is now 44.4, plus 0.2 times what actually happened in May. Well, that was 34, okay, 34, and then minus the same old 44.4. I get the forecast for June using this particular technique would be 42.3. The simple exponential smoothing forecast for June. Okay, now having that, we have enough to do July. Because in July, you would say, well, the forecast for June, which we just discovered, so to speak, was 42.3 plus 0.2 times what actually happened in June. Well, that was 48, minus the same old 42.3. That's the forecast for June. So I get that that is 43.4. And you're going, yeah, we need the forecast for August. Now we finally have what we need to determine what the forecast would be for August, because what pulled us up short is we didn't have the forecast for July. In simple exponential smoothing, each forecast is kind of daisy-chained into the next one, so we really didn't have any choice. When they told us March, this is what I mean by a surprising amount of work, we'd have to work through all those months to get down to July. Now we're ready to actually answer the question, because going back to the original question, the forecast for August, now we have the forecast for July, 43.4. That's where it belongs, right here, 43.4 plus 0.2 times, now 38, we had that actual this whole time, minus 43.4 again, the forecast for July equals 42.32. There, that's the answer. Using simple exponential smoothing with an alpha of 0.2, the forecast for August should be 42.32. Actually, you might get a slightly different answer. It'll only be slightly different, like 0.36 by a couple decimal places, depending on how you solved the problem. Because since these are all chained together, and they came out decimal places, if you stored the decimal places like out to 16 places, and you say, why would I store 16 decimal places? If you work it, for instance, in Excel, it'll automatically do that. You'll get a slightly different answer than if you put the numbers in one at a time on your calculator, which is kind of the assumption that I was using, because that's how I was working this problem, because that's generally what you wind up doing like on an exam. At any rate, that'll create slightly different answer here in terms of decimal places.